Good morning. Welcome to the April Town Hall. I appreciate everyone's attendance. This is an exciting town hall with Dr. Jeff Spitler. Before we get started with Dr. Spitler, just a few housekeeping and announcements that we'll go through. So just a quick few slides here. All right, some news and updates. There's a lot going on with IGSHPA right now, and hopefully you're on our mailing list. If you're not, send us an email at info@igshpa.org. We'll make sure that you're on the list. These town halls have been very popular, and also our Dig Deeper, our more technical sessions have been well attended. If you aren't aware of the listing, it's at the events menu at igshpa.org. So check that out. There's an event description and then registration links for the Zoom meetings at that location. If you're interested in submitting an abstract for a town hall or a Dig Deeper, send an email to info@igshpa.org and we'll take your abstract. We do have some openings this fall for town halls and Dig Deeper sessions. Just a reminder, the 2022 annual conference is in Vegas this year. It's December 6th through the 8th. We're partnering again with NGWA. We had a very successful conference last year with NGWA. And this is supposed to be their most attended conference in Vegas, so we're expecting good things. We do have already two sponsors, a platinum sponsor, Climate Master, and a gold sponsor, Grundfos. So if you're interested in sponsoring, you'll want to sign up pretty soon before all the sponsorships are taken. Same with booth space. We have a number of exhibitors already. If you go to the IGSHPA website, igshpa.org, and click on conferences, you'll see the buttons on there for registration as well as exhibits. We have an exciting change to this year's conference as well. We have a research track. Dr. Spitler is heading that up, and we're expecting really good speakers on the research track. So we'll have our normal residential, commercial, and loop installer / driller track, as well as a research track this year. Another announcement coming up at the end of this month is the NYGEO conference. That's April 27th and 28th. So if you're in that area of the country, that should be a really, really good conference, some good speakers, and lots of time to work together in that conference. Just a note on CEUs and renewals. We're no longer waiving the CEUs like we did last year. So if you'd like CEUs for the town halls or Dig Deepers, please send a chat message to IGSHPA. Sally Stevens, our member services coordinator, is logged on the IGSHPA account. So if you'll send IGSHPA your name and email address, we'll make sure you get CEUs for this town hall. Just some housekeeping here. We welcome questions at the end of Dr. Spitler's presentation. If you'll type your question in the chat window, then I'll read those at the end of the presentation, and we'll make sure that we answer as many as possible. If we don't get to your message today, we'll respond to you later on. And as always, please mute your microphone unless you're speaking. That way we're able to participate in this town hall. We are recording this session, and it will be posted on the IGSHPA website, so that you'll be able to watch it later on, or let your colleagues know if they weren't able to attend. So now to our speaker. Let me switch over to my quick bio here. We're lucky to have Dr. Jeff Spitler, PhD, PE. He is the Regents Professor of Mechanical Engineering at Oklahoma State University, where he holds the OG&E Energy Technology Chair. He has 30 years of experience researching ground source heat pump systems, with the results published in over 120 technical papers. He's a fellow of ASHRAE and IBPSA, and currently serves as editor-in-chief of the journal Science and Technology for the Built Environment. So we welcome Dr. Spitler, and thank you very much for your time. I'll stop my screen share and turn it over to you. Welcome. Thank you.
And Jeff, I hope I could take the speaker's prerogative to add one more announcement to your announcements, and that's for the research track. We're still accepting abstracts. So if you're a researcher, there's details on the IGSHPA website. You can just follow down to the conference, and there's research track info, including how to submit an abstract. And they're due April 18th, but if you're listening to me today and you need an extra day or two, I'll work with you. So, okay, thanks. Okay, so I'm going to talk about a study we did. It's now almost, or at least some of the data are 10 years old. It's also now the previous ASHRAE headquarters building. They sold it to the Children's Hospital. And they actually instrumented both a ground source heat pump system and a variable refrigerant flow system. And the talk today is about our findings on that. So I had a couple, let's see if we can get this to work. I had a graduate student at the time, Laura Southard, that did a lot of the work on the project, and also Dr. Xiaobing Liu from Oak Ridge National Lab was one of our co-investigators. We were supported by GEO and the Southern Company and the U.S.-China Clean Energy Research Center. Also had help from the ASHRAE staff, particularly Mike Vaughn. So let's just start off by acknowledging them. So this was the ASHRAE headquarters building here. It was originally built, I think, in the 1960s. And around 2008, there was a renovation. It included this addition of this sort of conference center on this side of the building. The building met quite a few of the standards for, it's a LEED Platinum building, Energy Star building, and I think it was an A- building on the ASHRAE Building Energy Quotient. And it was the idea when they renovated is they would create a living laboratory, and they put in over 1,000 measurement points. They changed some things. It changed to an open plan office design to have more daylighting. But really from my view, the main sort of innovation was in the system. So they had a variable refrigerant flow system serving the first floor of the building, a ground source heat pump system serving the second floor, and then also a dedicated outdoor air system. And the VRF system served about 17,000 square feet. There were a few areas on the first floor it didn't serve. Mainly it was office space, mailroom, and the learning center, which is only used some of the time. But I think the learning center can hold over 100 people, so that they had some meetings there, but infrequently used. Had 2 outdoor units, 28-ton nominal capacity, and 22 indoor fan coil units. So this is one of the outdoor FCUs. It's a paired unit, and this white piping you see on the surface is refrigerant piping that had to be piped outside for refrigerant safety reasons. The VRF system interestingly, had a single set point, and it tried to maintain the set point within 1 degree Fahrenheit, although there were thermostats with some paddles on them, so users could reset the thermostats up or down, but the system that tried to maintain set point, and typically individual units didn't seem to switch back and forth between heating and cooling, but you could often see adjacent units serving this open plan area where one was heating and the other was cooling. So there was quite a bit of that type of, well, I think wasted energy, but I guess that's probably a value judgment. So the ground source heat pump system, there's not so much to show because most of it's either underground or in the ceilings. I think there was one console unit in the stairwell, this unit here. There was a mechanical closet with a glass door on it. And this picture was taken through the glass door with 2 pumps and some pressure gauges and so on. But that's it for the mechanical room. There's no other room anywhere. So it served the entire second floor plus the rear stairwell, a little bit less floor area, mainly office space, and there's a couple of conference rooms. There were 12 boreholes, 400 feet deep, 14 water to air heat pumps with a total capacity of 31.5 tons. And the heat pumps were, when they were installed, I think were pretty much state of the art. They were 2-stage units with ECM fan motors and variable speed for the fan motors, although they operated at standard set points for each stage, or standard flow rates for each stage. The controls were staged. So first of all, there were heating and cooling set points. 68 and 74 were typical, though users could reset them. But unlike the VRF system, which was trying to maintain within 1 degree of set point, the ground source heat pump system could float between the heating and cooling set point. And if the temperature was exceeded by, if I remember right, 1.5 degrees, we put on the low stage, cooling or heating came on. If it was more than 2.5, the high stage, heating or cooling came on. So there's also a DOAS system, and it provided, I'd say, partly conditioned outdoor air to both floors. It was generally always lower than the room temperature. So in the summer, the DOAS system would actively be cooling. And in the winter, it wouldn't actively heat, but be recovering heat. So the outdoor air was warm some, but not up to room temperature. So generally speaking, the DOAS increased the heating loads for the other two systems and decreased their cooling loads. This is the DOAS system with what looks to me like a bunch of residential units piped into the air handler portion here. So qualitatively, and this was early on when we started getting measurements, the electricity usage began to be reported. Some people from, I'll just say the VRF industry said, oh, well, the loads are quite a bit different between the first floor and second floor. While we check this, the lighting and the plug load densities are nearly identical. The occupancy, we don't have a measurement of who was there at any one day, but the first floor had about 1 person per 400 square feet, and the second floor had 1 person per 259 square feet. And the learning center was used about 26 hours per month on average. But of course, that would increase the load on the VRF system when it was being used, but relatively small amount of time. The DOAS system, and I never found the reason for this, but it provided a bit more flow to the first floor than the second floor. So that would increase the heating load and decrease the cooling load. And the rooms then on the second floor, they have heat gains from the roof. The first floor has some more glass facade, but only some of it's conditioned by the VRF systems that were metered or measured. There was another VRF system that served the entryway, and it wasn't part of the measurement. So the net effect, which we will come to later, we measured the heating loads. The first floor has somewhat higher heating loads. The second floor has higher cooling loads. But in general, the cooling loads are quite a bit higher than heating loads, as you might expect for an office building in Atlanta, Georgia. So when we started on this project, there were the building had been operating for I think 3.5 years. Some of the data had been lost. There were some gaps in the data, so we picked a period starting with July 2011, where we're starting to get good data, and we used that. It turned out that the VRF system in April of 2012, the manufacturer changed the control board. And that changed the flow rates. And since we were using flow hood measurements made during commissioning, we weren't able to recover from that. So the actual comparison goes for the first 9 months. But we have, say, good measurements for the ground source heat pump system for the whole 2 years for the heating and cooling provided. So I'll be presenting that. So the electrical energy consumption for both systems was measured. The heating and cooling loads were, how shall I say this? They were measured. We had temperatures, inlet and outlet temperatures, and flow rates from the flow hood measurements that were tied to each stage of operation. So we could reconstruct how much flow there was. And that allowed us to get the heating and cooling loads. And then we also computed what I now call performance factors, but we called the system coefficient of performance and energy efficiency ratio. And then we're going to discuss why this happened. So the presentation's a little bit in the same order that we did the research. So first we'll look at the electrical energy usage, and we can make our own sort of judgments based on that. And then we look at the loads and finally this system performance metrics. So the monthly energy used per square foot, it is here. And you can see in July of 2011, the ground source heat pump system used a little bit more kilowatt hours per square foot. And every month after that, the VRF always used more energy. So, I mean, again, of course, depending on the loads, maybe there's an explanation for that, but we'll come to that. If you, some of the results I'm going to show you are what we call a binned analysis, where we take like here, say, these points would represent the VRF system energy consumption in watts per square foot for all the hours, maybe between 54.5 and 55.5, or I think we might have had slightly smaller bins. Maybe it was 54.75 and 55.25. But and then this black line is just a sort of fit to the data, but you can see that the VRF system uses about, at cold temperatures, uses about 3 times the electrical power of the ground source heat pump system. And, you know, as it gets warmer, it uses less electricity, and there's sort of a, maybe a shoulder region when it's at a minimum value for energy consumption, right? And the actual minimum values vary with the ground source heat pump here in the VRF system. But notice around, say, 50 to 55 degrees, the ground source heat pump system is using about 0.2 watts per square foot, and the VRF system is using about 3 times that. And in Atlanta, there's a lot of hours in this region. So that's, you know, that's one of the reasons why there's just so much difference in the performance. And then as it gets, we get into the air conditioning season, we see the energy usage go up for both the VRF and the ground source heat pump system, as we'd expect as we get more cooling loads, and not quite as much difference there. Finally, the green is the DOAS system, where you can see that when it's cold, it's not, there's no vapor compression cycles running. It's just recovering heat, so its usage is pretty constant. And then as it starts to get warmer, the cooling units start to come on, right? So it provides a certain amount of the cooling is provided that way. So to try and explain some of this, just have an example from what I call a moderate day. So it was April 2013, it was 43 degrees in the morning and 63 in the afternoon. We still have cooling loads in a building, office building. But if you plot the power usage for the day, right, there's setback thermostats at night, and in the morning you see that and again, this is watts per square foot of floor area, right? You see this little blip up where probably one heat pump is coming on, another little blip up where one heat pump's coming on, and then in the morning we get a few heat pumps, maybe three heat pumps come on, and then maybe we drop down to 2, and you know, but it's pretty typical. We're not running all the heat pumps that we have. We're only running a few at any one time. Whereas the VRF system goes, you know, from near 0 to quite high all of a sudden, and that's because the VRF system during the day, all the units are running all the time for the most part. It's not exactly true that they're always running all the time, but could say almost all the units are running almost all of the time. So in the ground source heat pump, the zone temperatures are here. So you see in the morning it was cool-ish, and the deadband control between heating and cooling let the temperature sort of float up over time. Whereas in the VRF system, the units that were in cooling are here. What is it? There's 6, I think. You know, their temperatures, they fluctuate some, but they're relatively constant over the day. You know, here's a case where we were cooling one zone here, and the zone next to it was heating at the same time. And these, you know, in an open plan office, so they're exchanging cold air and hot air. And so we see these units are cooling, these units are heating, and you know, they just run all the time. So that's a lot of, I'd say that's a lot of the cause of the differences in electricity consumption. But we are going to set that aside and say, okay, if the cooling and heating was really needed to maintain comfort, what's the system performance like? So we kind of set this control strategy aside when we get to the system performance. Okay, so the ground source heat pump system uses electricity, and the question is why? And I'm going to talk about the next part. We're going to talk about the reasons. You know, of course, the source temperatures are better. I won't actually show you any plots on this, but generally the rated equipment efficiency at the actual source temperatures was better for the ground source heat pump equipment. And then we have this apparent control issue with the VRF units running most of the time, even under moderate load conditions. And I'll say unnecessary simultaneous heating and cooling, but I guess you could say that's arguable. Maybe it's really necessary to heat in one zone and cool in the zone next to you to maintain some user desired temperature. So, and then of course the loads are different, but how much different are they? And we need to dig deeper in that. And that's what the rest of the study goes into, these details. So of course, these are the source temperatures. So the blue dots here represent the returning ground heat exchanger temperature over time. You can see it's very moderate. It peaks around maybe 85 degrees, and the minimum is maybe somewhere around 65 degrees. And of course, the red is the ambient air. And as always, it varies a lot more than the ground temperature. In terms of, to really dig into this, right, the real question for me is how much heating and cooling are we providing with each system, right? Whether we want to argue about whether the VRF system had to provide as much as it does, this is what it provided. And we base this on measurements. I'm leaving out, I cut this down to try to get my talk into 45 minutes, but it's based on flow rates measured during commissioning, measured temperatures and humidities. And the flow rates measured during commissioning were measured at different thermostat stages so that we could, later, when the system was operating, we knew what stage, each stage it was at, so we could then determine the flow rate. And that was true for the VRF system up until April 2012, right? And they changed the control board, the flow rates changed, and we missed that and weren't able to continue the VRF analysis. So there's a detailed uncertainty analysis. It's covered in the second ASHRAE Journal paper. There's some bibliography at the end, but it accounts for the errors in the sensors, also some of the approximations. So for example, we had zone relative humidity measurements, and we had to use that to estimate the entering air relative humidity to the heat pumps. Also accounts for aggregation. So if you have random errors in different units, but you're measuring, say, 10 units, then that reduces the uncertainty in the total. So the final uncertainties for cooling for the ground source heat pump were about plus minus, say, well, it's 14% on the plus side and 11% on the minus side. For heating, it's about plus minus 7%. And the VRF system, the uncertainty is lower, and that's because all the units were running all the time. So we had, we get this aggregation issue that reduces the amount of uncertainty. So I show some error bars here for our results, but this is the monthly heating provided. You can see in this first winter, the VRF system, it's providing more heating than the ground source heat pump system. And well, you can see here, we've got the ground source heat pump system for the second year. Then the cooling, monthly cooling for the ground source heat pump system, it's generally higher. And if you compare the scales on the two slides, you see there's the ground source heat pump system is, say, at peak is providing much more cooling than the difference in heating on the previous slide. The ground source heat pump system, I'll say it's providing more cooling in the summer months, but in the shoulder seasons, you see actually it's providing a bit less. And I think this again goes back to the thermostat. So if you look at the 9 months that we could actually compare both systems for, right, the cooling was provided for the ground source heat pump system was a little bit more in terms of thousands of BTUs per square foot than the VRF system, and the heating's somewhat less. So there's 62% less heating than the VRF and 6% more cooling. So the way we typically characterize the performance of the system is either, the coefficient of performance, in this case, integrated over time. So again, I'd probably call this a performance factor now, but so it's the ratio, what you're getting, the heating divided by what you're paying for the electricity. And you can see that the ground source heat pump system compared to the VRF, right, this is roughly a COP of 3 over the season, and the VRF system's roughly 2 over the season. So it's significantly better for heating. Another interesting aspect is this change from this winter of 11, 12 to this winter, you see that the GSHP system goes up from about 3 to about 4. And we're going to come back to why that is a little bit later. Okay, so if we plot or also show the EER, right, and this is in American units of BTUs per hour or BTUs per watt hour, right? So that's why these values are so high. If you want on a dimensional basis, you'd have to divide by 3.4. Right, the ground source heat pump system is quite a bit higher than the VRF system from month to month, right? And yeah, well, there's reasons for that, right? Some of them are simply related to the source temperatures, and also probably doesn't appear the equipment's quite as efficient as expected. So if we take again, now go to a binned analysis and look at the performance of both systems for cooling versus the outdoor air temperature. You see something that I found very interesting when we started studying this. That is, generally, as it gets warmer outside, the system performance gets better, right? And, you know, from a thermodynamic, you know, I teach thermodynamics, you know, we generally tell students, oh, well, if the source temperature or gets higher, right, or that we're trying to reject heat to for the same inside conditions, you know, the COP or EER should go down, but in fact it goes up and then flattens out when it's fairly warm. The VRF system, you see it goes up and it comes back down just a little bit. Heating performance is a little more, you know, for the ground source heat pump system, it's looks fairly flat with temperature, but of course it's not exposed to the outdoor air temperature. The VRF system, the COP actually climbs a little bit as it gets colder. And I thought we might see defrosting, but it doesn't, the effects of defrosting, it doesn't really show up very clearly. I mean, maybe this is, you know, these higher points or lower points in here maybe are defrosting, but it's a little difficult to say. So we've got somewhat I call counterintuitive trends. You know, first of all, the ground source heat pump system heating COP goes up from one winter to the next. Even though if you look back to the source temperatures, you see they didn't change very much in the ground loop. You know, we have both systems increasing their cooling EER with increasing outdoor air temperature up to a point, and then they drop a little bit. And certainly for the ground source heat pump system, we can see the performance increasing with higher loads, and I'll show you, I'll come back to that in a minute. So the ground source heat pump system, this increase from the first year to the second year is related to the pump control. So this is a central pumping system with a control by differential set point on the loop. And up until partway through that, between the two winters there, the set point was set to 20 PSI difference between the two. And an engineer who's since passed away, Kirk Mesher, was expert on ground source heat pump system design. He was at ASHRAE headquarters and looked at the gauge in that mechanical closet and said, oh, this setting's way too high. So they changed it down from a 20 to 8. We went there in, I think it was 2014 actually, and we made, with some help from the Southern, an electrical engineer from Southern company, we made some measurements. We changed the set point at 8. I don't remember why we had 15 instead of 20, but that's what we had. And then we tracked it as the flows changed. And you could see at 8, we're using, say, somewhere between around 300 watts and maybe 600 watts. And at 15, you know, we're using more like 800 to 900 watts. So, of course, if you increase the flow by increasing the pressure, the differential set point, you will make the heat pumps a little bit more efficient, but you're then also spend more electrical energy on pumping. And we've got, we estimated the energy consumption. It's a little hard to see, but if you, the purple here would be the heat pumps themselves. The green would be the fans. The red is the pumping, right? And you can see it drop quite a bit from 2011, 2012 to 2012, 2013. So that's one of the reasons why the heating COP went up from one year to the next. And I found this quite interesting because this building, being in the ASHRAE headquarters, the owner was quite knowledgeable. They had really great maintenance staff. It had been commissioned, and still roughly, the COP going from 3 to 4, or a 33% increase, was sort of left lying on the table. It's something to think about. In general, we found that the performance went up when the load got higher. So first, earlier, we plotted the EER versus the total monthly cooling provided. You can see in general, the months where we have more cooling, we get a higher efficiency. Same thing if we bin the analysis. I did this, I think, last year. Plotted the performance factor. So this is the total heating and cooling provided divided by the total electricity. So we blended the heating and cooling together, and we plotted that against the total heating and cooling provided. And you can see the performance factor just goes up, and flattens out as we get to a relatively high runtime fraction, right? And so if we go back a few slides, there was this blue here. It's what I'm calling a parasitic load, right? So the pump controller uses some watts of electricity even when the pump's not running. The heat pumps use, a very small amount of electricity, 10 watts or 12 watts or something like that when they're not running. And those factors come in. And then there's also the fans run all day, even when for the ground source heat pump system, even when there's no cooling or heating being provided. So those things tend to make the overall system performance drop as we get to lower load conditions. Same thing was true for the VRF system. This is some speculation based on some other research that's been done, and that is that the simultaneous heating and cooling, it's often advertised to be one of the great features. It may not be as efficient as imagined. If you're going to provide heating and cooling, you have to keep the refrigerant temperature in the condenser has to be higher than it might be otherwise. And that's maybe not as efficient as imagined, but I say it's speculation. We don't have those kind of measurements for the VRF system. So in terms of conclusions, right, the ground source heat pump system significantly outperformed the VRF system. And for the 9-month period where we could compare them, right, you can see that the ground source heat pump system had over 50% higher heating COP. And I think it was something like 60-some% higher. I'll try to do the math in my head, but it's quite a bit higher EER than the VRF system. So why is this? Well, right, of course, the ground source heat pump system has more favorable source temperatures. I think that's one of the things we always think about and been saying for years. And it's true, but it's the whole story is a little more nuanced than that. In terms of why the performance, at least the electrical energy was higher, right? We have this issue with the VRF units running most of the time. It doesn't really answer, this apparent control issue doesn't really answer the question of why COP and EER are higher, right? Because the cooling provided is included in the VRF analysis. And also we have this, this the parent control issue also shows up as apparent or apparently unnecessary simultaneous heating and cooling, right? And then if we assume, as we did in the COP and EER analysis, that all the heating and cooling that is provided is needed, right? We've got higher ground source heat pump unit efficiencies, rated higher efficiencies, and then the actual efficiency of the heat pumps is significantly higher. So all those things add up to improve performance for the ground source heat pump system. Okay, so looking forward, I thought I'd take this opportunity to discuss some more recent research and even where we might go in the future. So, I have my observation that even though this is the ASHRAE headquarters building, had knowledgeable owner and maintenance contractor, the manufacturers of the equipment knew that the performance was being analyzed and was publicly available. all these things were known, and yet the heating performance was still suboptimal. It was still better than the VRF system, but it ran 5 years with this relatively high set point. So I find that very interesting, and I don't think it's a knock on ground source heat pump systems. I'm sure other systems don't always run as optimally as they could. So my view is that measurements like this should be common, not rare. When I say measurements like this, I mean of the system performance. I don't mean that I don't mean that I should get a bunch more contracts to do these sorts of studies, because I think it's too expensive to make it common. It has to become more of a standard way of doing business. The Internet of Things, it's lowering the cost all the time of making these sorts of measurements. A lot of the needed measurements, they're actually already being made. They may be internal to the heat pump. They may not be available to the owner of the heat pump, but they could be. Also, I think that standardization of the measurements and analysis procedures should lower costs. So one of the reasons why a study like this is so costly is because there's a lot of human effort after the fact to make up for the fact that we don't have maybe all the sensors that we need. So I think if we planned ahead and had a better idea, we could lower the cost. And it's my own personal hope that this becomes much more common in the future. I, of course, also believe it'll show ground source heat pump systems are usually better than the alternatives, but whatever it shows, I'd like to know. So I've worked actually for about the last 4 years on an international collaboration project with the International Energy Agency Heat Pumping Technologies, what's called a Technology Collaboration Program. And this is the specific project they called Annex 52. There were 7 countries involved. So besides the US, it was Sweden and the Netherlands, Great Britain, Finland, Germany, and Norway. The project ran from 2018 through 2021. I'll say it's almost done. We've submitted almost all of the reports. There's still we just submitted the draft final report to the HPT Executive Committee. So most everything's online, but there's just a few more things to come. The focus is on ground source heat pump systems, but as one of our members commented on multiple occasions, almost everything we did in terms of methodology could be used on other systems like the VRF system. So I think we've systematized a lot of the nomenclature methods. We have a new boundary schema. There's an annotated bibliography with more than 80 publications on, these would be on large scale, so commercial, institutional, multifamily buildings, large scale ground source heat pump systems. We've identified standardized new what we call boundary schema, so we could look at the heat pump performance or the ground loop performance separate from the overall system performance. We have published some guidelines on instrumentation and measurement, and also on sort of data, collecting data and archiving it, processing it, and how often you need to measure and things like that. We produced a guideline on calculation of uncertainties. So we have about 40 case studies. I think actually a few more have come in since I put this slide together, but there's about 40 of these measurements of ground source heat pump systems. We have, I think, 3 open access data sets where we have the data actually published in online archives, something like 17 papers. Case studies, here's the Atlanta one that we discussed today, but the other ones are spread throughout Britain, Netherlands, Germany, and also Scandinavian countries, Norway, Sweden, and Finland. So there's quite a bit. If you'd like to see more measurements on ground source heat pump systems, it includes systems with closed boreholes, groundwater systems, and also energy pile systems. There's quite a bit of reading there. You can find all this at the website. My colleague at the Swedish Geoenergy Center, Dr. Singhal Jalin, was what's called the operating agent, and I served as her factotum and as the co-operating agent. So there's a bibliography. papers available, some published in the ASHRAE Journal. There's a final report. There's been some later papers published here, and then also the case study report from the annex. So with that, I will wrap up, and Jeff, I'll be glad to take any questions that we have, if any have come in and everyone hasn't fallen asleep.
No, quite the contrary. There are quite a few good questions here.
Okay.
Thank you, Dr. Spitler, for the excellent presentation. That was really informative. I'll just start at the top. The first question is, are we able to get copies of the slides after the presentation? This is recorded, so there will be a video online on the IGSHPA YouTube page. If you go to the IGSHPA website and then click on that YouTube button at the top, you'll find the video. If you'd like a copy of the slides, Dr. Spitler has provided a PDF version for us. So just simply send an email to info@igshpa.org and we'll send you that PDF. Next question, Bob asks, given that winter peak demand, the coldest day for VRF is 3 times higher than that of GSHP, it seems like a given quantity of electric grid capacity would be able to support 3 times as many buildings heating with GSHP than with VRF. Is that a reasonable conclusion?
Well, okay, so this was Atlanta, and I'm pretty sure the utilities there are summer peaking. So, yeah, quite possibly, but I think, one caveat to the study is it's two systems. So I'd be a little loath to say testify before Congress that it was that it would be true in places where there are winter peaking utilities. So it may be true, but I really think we probably need more measurements to show that. So.
Okay, thank you. The next question from Jeff is asking about the DOAS units feeding the geothermal units and VRF, and it looks like Dan Ellis answered his questions. The DOAS is ducted into the returns of the VRF fan coils and into the returns of the water source heat pumps. Excellent question there.
For the most part, there's a few that weren't ducted in, but I'll just say that was accounted for, the fact what the return conditions were. So.
Okay, thank you. Tom asks, do you have the long-term electrical usage on GSHP versus VRF to at least look at it from a macro level, long-term energy use? I say this with the understanding that there are many variables to consider, but it would be great info for companies to use in an elevator pitch.
Okay, so I'm trying to figure out, we have, for the 2-year period, we have electrical energy use, I think, on a 15-minute basis. We don't have data longer term than that. So I think that's how I'll have to answer it. But so. Okay.
Very good, thank you. Dan Ellis also commented here that he has the full set of mechanical plans on hand. Rick and Judy ask, the ASHRAE ground loop seems to average above outdoor air temperature mean. Can you hypothesize on the increase in cooling efficiency and reduction of heating efficiency if there is some spring thermal bleed opportunity added, such as sidewalk, parking, snow melt, or other shallow loops explicitly for heat loss?
Can I hypothesize? Well, I'll say one thing is the system doesn't show some, even though it's rejecting a lot more heat than it's being extracted, it doesn't show a lot of signs of long-term temperature buildup, right? And we did have some temperature measurements earlier. So there could be, but it's only, let's see, 12 boreholes or 14, I can't remember. There's 14 heat pumps and 12 boreholes, if I remember right. And it's not a large compact field, so I'm not sure it has the potential, quite as much potential for those sorts of applications. It might, it's something I'd have to look at further, but.
Very good, thank you. Just a reminder, if you're looking for points for your CEUs, please send a chat message with your name and email address, and we'll make sure we record those. I don't have any other questions at the moment. Did you have any other comments? Oh, here, just one came in, perfect timing. Chuck asks, is it possible that one of the VRF's disadvantages is due to the fact that the extensive pumping of the refrigerant around the building must be done via a compressor type device versus a real pump in quotations, like a centrifugal water pump that moves mass around the building more efficiently.
Yeah, I think there's all kinds of things possible, but unfortunately, VRF system, they have a lot of data going back to the manufacturer, but we didn't have access to it. So it was a little bit beyond our purview to find all, sort of find all the reasons, but there's, I'll say, several possibilities. And as I think I mentioned, one identified in the literature was this, maybe the pressure difference between the condenser and evaporator being held higher than it would need to be, so that it could provide both heating and cooling, as compared to if it was only providing cooling. So, but there could be several things.
Very good. Thank you. Bob asks if you could back up to the slide showing annex with data on the heatpumptechnologies.org.
Was with the
I believe that's the one.
Yeah. If you just want to get the website.
I think it's the website. Yeah.
And all the other links for the other documents, they're all on that website. So if you start there, you can find everything else.
Okay. Very good. Tom has a question. If available, would you be interested in looking at VRF versus Geo in the Cedar Rapids, Iowa area? I may have a customer that has similar buildings with both that may be okay with monitoring.
Yeah, well, get in touch with me, I guess. I would say. So in fact, my email address is on this slide too. So.
Okay, excellent. Really, really good questions. I don't see any more right now. We still have plenty of time. It's 11:18 Central Time. So if there are any other questions, feel free. In the meantime, if you have any comments based upon the feedback, Dr. Spitler, we would certainly welcome that.
Well, I guess I won't try to speak off the cuff now with more detail, but okay. I'd encourage you, if you're interested in these sorts of measurements, the Annex 52 has a lot of measurements. Limitation being they are all focused on the ground source heat pump systems. They're not really comparative measurements there. Jeff, I think I see a hand up from Carl Oreo. So I don't know if you can.
Thank you for noticing,
Carl.
Yes, can you unmute, Carl?
Can you hear me?
Yes.
Okay. We're seeing VRF tying into geothermal now. Do you have any thoughts on what that's going to do to the overall efficiency of the system? Are we headed towards earth coupling to VRF?
Yeah, good question. I mean, these systems have been available for a while. There was actually, I think, so back to the annex for a minute, Oak Ridge National Lab actually did some monitoring of one of these systems. Unfortunately, I don't remember which system it was. I don't really know if it's going that way market-wise or not. I mean, of course, it's certainly possible to couple any cooling technology. I think, well, maybe not. Most cooling technologies could be coupled to ground source, but I don't have any insight as to the market, in terms of what's going on, if this is really becoming more common. So,
okay. Thank you for that question, Carl. Clifford asks, is the difference, I'm sorry, it's scrolling on me. Is the difference in loads and usage simply due to the second floor load being higher for the ground source heat pump system?
Well, I think no, I think the difference in loads, of course, there's some physical differences, like the second floor has, sits up right underneath the roof. I think the biggest difference in loads is probably due to the fact that the equipment's being run all the time in heating and cooling mode. And so, I mean, you could say it maybe not the definition of like the design cooling mode, right? Where we're just looking at that, but in terms of the loads on the equipment, the controls are actually forcing it to run different units to run in cooling and heating at the same time. I think most of the differences are probably due to that fact. So,
very good. So would it be fair to say that the VRF operates more like a central system, and the water source heat pumps operate more as distributed systems from a control standpoint?
Well, I mean, I think in one sense, you know, if you wanted to ruin the ground source heat pump performance or make it worse, right, you could have actually done something similar. You could set all the set points to be the same and have no deadband, you know. I mean, maybe you could have done that, but the ground source heat pump system runs like, sorry, what I would say a typical control strategy. And it just didn't create this sort of excess, you know, everything running all the time and cooling one zone while the next unit 10 feet over, you know, you're blowing cold air out of one diffuser and hot air out of the other diffuser. So.
Very good. All right, we do have some more questions here. Dan asks, what are your observations on the sizing of the ground heat exchanger? It was relatively short in length per ton of connected heat pump capacity.
Yeah, but it seems to work pretty well. So, I mean, I'm not saying anybody made an error by making it that big, but now you look at it and say, oh, we probably could have made it smaller. So, but yeah, it works pretty well. So.
Along those lines, Garen comments, thermal conductivity 1.88, deep earth temperature at the site 67 degrees Fahrenheit.
Yeah. Garen would know since Eubanks did the original thermal conductivity test that we used when we were not so much for this because we were more focused just on the system performance, but we also did some modeling and so on, and then we used that thermal conductivity test.
Very good. We still have some time here for more questions. Matt asks, I may have missed this, but were there similar simultaneous heating cooling issues with the GSHP due to an open floor plan like you observed with VRF?
Well, it may have occurred sometime. I mean, I think it certainly occurred some hours, but the number of hours was very few. And having this nominal 68 and 74 set points tends to, you know, to reduce that strongly. So.
Okay, thank you. Bob asks, how would one design a VRF system to make it, in quotes, geothermal ready, i.e. easier to recouple to ground in the future or to run as a multi-source system?
Well, in terms of coupling to the ground, right, you have, instead of the outside unit that, you know, you need a raised plate heat exchanger or something instead of a fan coil or fin tube heat exchanger outside. But other than in terms of making it dual source, yeah, that's sort of outside my, I mean, I could tell you thermodynamically how it'd be done, but I won't try to give you a practical answer on what's involved. So.
Very good, thank you. Jeff comments, there are units in Daikin that have ground linked VRF. Andy mentions Mitsubishi also have ground source VRF. Flow requirements prescribed by the manufacturers for some reason always seem to be far higher than a GSHP, and so parasitic pumping power is often high. Any comments on that, or should we move to the next question?
The comment is, that's interesting. I if there's any more information about that, I'd be interested, but no, that's news to me, so thanks.
That is interesting. Yeah, why that would be, that's a good question. Bob asks, if GSHPs are more efficient, why hasn't ASHRAE replaced their inefficient VRF system?
Well, I can't really speak for ASHRAE, but I think you can imagine this is a high profile building that they then sold. So I wouldn't want to do it or speculate on an economic analysis of ripping out a VRF system that works and putting in a GSHP system and what the payback would be. So.
Very good. Victor asks, where could one find the recording to this presentation? Within the next couple of days, if you go to IGSHPA.org, there's a YouTube icon button at the top of the website. If you click on that, that will take you to the IGSHPA YouTube page, and you'll find the recording uploaded to the website. Don't see any additional questions at this point. We have about 4 minutes left. I want to be respectful of everyone's time. And thanks again, Dr. Spitler, for the great presentation. Excellent exchange of information here. And we look forward to the next town hall and dig deeper section. Thank you very much. Have a great rest of the week.
Thank
Bye.
you, everyone.